In this video, we're going to explore the domain and range of a function, and we're going to look at some piecewise functions. So when we talk about the domain, we want to think about is the values that we can put into the function. We call them the inputs, we call it the argument, we call it the independent variable, and we call the range what comes out. So are they dependent outputs is another way to say it. Now, if we are looking on the xy plane, then the domain would be the x values, and then the range would be the y values. So what we want to think about when we're doing a function is that we have some sort of information that's going to be coming from the domain. It's going to go through the function, and something's going to be coming out with a range. So A will go in, and maybe it'll go to y, and B will go in, and maybe it'll go to x, and C will go in, and maybe it'll go to z. So that's how we're going to think about domains and ranges. What we can put in, what's allowable for us to put in, and then the range would be all the possible outputs that could come out with those inputs that we put in. So the way that we can describe the set of values for a domain or range or sets in general is we can use the verbal method. We can use a sentence to define the set. We can use the roster method, and the roster method is really good if I only have a couple of elements, a couple of items in my domain or range. We use set builder is another way of doing it, which kind of combines the verbal and the roster method. And then, of course, we could use the interval method, which we will do as well. So here's an example in which we have a verbal, the set of all numbers less than or equal to 6. We have a finite set of items in our set, so we can list it out with a roster method. Now, if I want all real numbers less than or equal to 6, then there is no way I could put that in the roster method because there's an infinite number of numbers, even between 5 and 6. So anything less than 6 real number-wise, I wouldn't be able to do the roster method. But I could use the set builder method on that. I can also do the interval method, which, again, I will show you in just a moment. So here's some things as we're looking at numbers. We should talk about what numbers are in terms of the notation and what it is. So our first number we're going to talk about is the empty set. And we can denote it with a 0 with a slash. I know computer science people are like, that's how I denote 0. Okay. Really, when you do that on a test or any kind of assessment in math, that means the empty set. That does not mean 0. So please refrain from using this notation for 0 because it does mean empty set, and you may be marked incorrect when you are wanting to write 0 and you're writing the empty set notation. Another way you can write the empty set notation with the curly brackets with nothing in it. And then also, this is the third way you can do it, is you can do curly bracket x. Now this bar means such that. Mathematically, that word there means such that, that straight up and down bar. And then I'm telling you that x cannot equal x. So that's one way of showing the empty set. Let's go back up here and look at the set builder. So I told you the straight line up and down can be replaced with the word such that. X, so the variable I'm declaring is x, the straight line is such that, and x is less than or equal to 6, and x, this funky looking e, is element or belongs to, and this w with the double bars means whole numbers. Well, what's a whole number? Whole numbers are 0, 1, 2, 3 on up. Natural numbers, here's the script for natural numbers, and it's 1, 2, 3 on up. These are the ones that you usually use when you first learn numbers, unless, of course, you've got an older brother or sister who says, would you like 0 pieces of candy? And you're going, yeah, I want 0 pieces of candy. And they're like, ha, 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 you get nothing. So natural numbers is what we learned first. Would you like 1 piece of candy? Whole numbers is if you have an older sibling that says, or cousin that says, hey, you want 0 pieces of candy, and you get all excited and you realize 0 means you don't get any candy. Integer is the next one. It's a z. And so we have the integers, which are -3, -2, -1, 0, 1, 2, 3. We pick up the rational numbers, which means that we can write them. Rational number means it is a fraction. Or any number that can be wrote as a fraction, or a decimal number in which it either repeats or truncates. In other words, it ends. And we use Q. We have irrational numbers. That's P. So we're picking up irrational numbers. Real numbers is all of the numbers prior to, and then the last one is the complex number. So if we were to do number sets, I'd say complex is the largest set. Of course, the empty set is the smallest set, and the next set above the empty set is the natural numbers. So mostly in this class, we're going to be working with real numbers. Occasionally toward the end, actually when we're in polynomials and we're trying to find zeros, we may come up with complex numbers. You might have heard them as imaginary numbers, but we're going to call them complex numbers. And we're not going to typically use the roster method. We're going to be using set builder notation or interval notation. Now, interval notation is used for real numbers. For us, we're going to use interval notation to use real numbers. So if in words, I want all real numbers less than 6, then my set builder, I can't use roster because it's real numbers, it would be x or any other variable I choose. I'm going to choose x, such that x is less than 6 and x belongs to the real number set. So there it is in set builder. In interval, I would use a parenthesis for negative infinity, and I would use a 6, and I would use a parenthesis because I don't get to include 6. Now, if I included 6, what would happen if I said all real numbers less than or equal to 6? Then it would look something like this. It would be the curly bracket x such that x is less than or equal to 6. X belongs to the real numbers. And in interval notation, again, we don't include infinity, and we go up to 6, but now we use a squared off bracket, showing that we have inclusive. So you'll hear me say inclusive or non-inclusive. This is non-inclusive of 6. This is inclusive of 6, and I know it's inclusive. If I look at my set builder, I have the less than or equal to versus non-inclusives. I don't get to include the 6, and there's no line underneath there. So here's some examples of what it would look like as an inequality and interval notation. This is for real numbers. Here's what it would look like on the number line. And of course, here would be a verbal description of all of the various inequalities that you may come up with. So all of this is building up to being able to talk about domains and ranges using the correct notation. So pay attention to when we have one side is equal to and one side is not equal to. So you could see that A is not equal to X, but B could be, X could be equal to X. So it is a parenthesis on one side, a bracket on the other. If they're both inclusive, then we have brackets on both sides. So how do we do this? Well, if we are trying to determine the domain and range, we exclude anything in the domain that results in division by 0 or results in, if we're trying to stay in the reals, that will result in something that is a non-real number, so it's a complex number. In the domain, we're going to exclude anything that, like I said, anything that produces a non-real number. We're going to look to see what our valid inputs could be, and that's going to tell me what my valid outputs could be. We can also look at the graph and determine the domain and range. So if there's a denominator in the function's formula, set the denominator equal to 0 and solve for it. That is going to be the restriction. So those are the things going to be divided by 0. If the function's formula contains an even root, so a square root, the fourth root, we set whatever's underneath the radical equal to greater than or equal to 0 and then solve. Now what happens if I have something that's a combination? So here's my function, f of x is equal to x minus 1 over the square root of x plus 2. If I just used the first part that says, hey, set that denominator equal to 0 and solve. So I have the square root of x plus 2 is equal to 0. I square both sides. I get x is equal to negative 2. So this tells me what my restriction is. So x cannot be equal to negative 2. And if I just leave it like that, then of course I'm going to make sure I'm not dividing by 0. However, I also have this radical that says, wait a minute, I got to make sure that whatever I put into my function is not going to produce a complex number because we're trying to stay in the land of reals. So not only does it have to be not equal to -2, but my radical, which is x plus 2, simultaneously has to be greater than or equal to 0. So x has to be greater than or equal to -2. Now, if I combine these two, that means x strictly has to be greater than -2. So my domain in set builder notation, which is my preference, is x such that x is greater than -2. X is an element of the real numbers. Now, because we are making the assumption that we're in the land of reals, if you would like to just shorten this, because we make that assumption, I just want to not greater than, you can do that too. I would be totally fine if you put that on one of my assessments. The other thing we want to do is in interval notation. Well, interval notation would be -2 to infinity. Notationally, these mean the same thing, just one is presented in interval notation, one is presented in set builder. And I want you to be able to be fluid in both of these. You got to be able to say, oh, this is what she has. I'll see this in the textbook. This is how I like to write it, or this is how it's wrote. What does this mean to me? So you need to be able to read both set builder and interval notation. So on these, we're asked to determine what the domain and range is. Well, let's focus in on the domain first. Now, the domain of this is I'm looking at this point in my math life is I'm looking for two things. I ask myself, does the function, meaning it, a even radical? If the answer is no, no restrictions for that. Now, the second question I ask is, does it, meaning the function, have the variable in the denominator? If the answer is no, no restrictions. Now, at this point, that's all we need to look for. Later, however, we will look for further restrictions. Those are the two questions I ask myself. Do I see an even radical in there? No. Does it have a variable in denominator? No. So I know if my answer to both of those are no, then I have no restrictions. And so I'm going to write my domain. So I usually like to declare my domain with a D as x such that x belongs to the real numbers. And my range, I usually like to do R. I actually like to subscript my function. These are functions of f. And here you can do it one of two ways. You can write it as f of x such that, and if you're not familiar with this as a transformed parent function or the toolkit of functions, which is square root, which has gone up 1, it would be f of x so that f of x is greater than or equal to 1. That's one way of writing it. In set builder, because we can use y as a replacement, I can always replace f of x with y, as long as y is not the independent or the argument. So I can use y such that y is greater than or equal to 1. Interval notation, so if I wanted to use interval notation, this would be -infinity to infinity. And my range for my function f would be, of course, inclusive of 1 and then going up to infinity. Now, if you're not certain where I got that from, please consider, and you're like, well, wait a minute, you said I can't always use my graphing calculator. The answer is yes, you don't get to use your graphing calculator. But at this point, we're just really trying to make that connection between the function and the graph and the domain and range. So if you need to answer some of these on your homework by looking on Desmos or a graphing calculator, I'm okay with that. I will give you something that will be easy to determine the range if I ask for that. But the domain, you should be able to come up algebraically without looking on the graph. So that's the first one. So let's take a look at the second one. Now, I have a square root. Okay, so we set the square root, which is the square root of x squared plus 4. We want to take the x squared part plus 4 and make it strictly greater than or equal to 0. Now I've got x squared is greater than or equal to -4, and this is true all the time. Any number squared, even if it's a -62, When I square it, it will be positive. So this is true all the time. So even though I have a radical that is even, I have a square root, I actually didn't pick up any restrictions in my domain. So my domain, again, domain of f, will be x such that x is an element of the real numbers, and my range of f is going to be y such that y is, oh, well, wait a minute. Y has some restrictions. My output has some restrictions. So you're thinking, okay, well, what's the smallest number that can come out? Well, the smallest number that can come out is if I put in 0 for x, the smallest number can come out would be the square root of 4, which is 2. So y is greater than or equal to 2. Interval notation, negative infinity to infinity. Interval notation here is 2 to infinity. All right, so now let's take a look at C. 2 questions. Do I see a radical that is even? No. Do I see x in the denominator? Yes. So I'm going to pick up a restriction. So I have x minus 2 is equal to, and I actually like to do not equal to 0. So x cannot equal 2. So that is the restriction on my domain. My domain of, or g, this is g this time, is x such that x does not equal 2. Now we're assuming that we're in the land of real numbers, so I'm not going to write an element of reals. You can, absolutely can. Interval notation would look like this. This is where I don't like interval notation. So negative infinity to negative, or to positive 2, excuse me, to positive 2, union between 2 to infinity. Doing this with the non-inclusive is saying I'm going to get really close to 2 on either side of 2, but I'm not going to include 2. So what about the range here? Well, this is one of those ones that we're going to explore further in this class. So it'd probably be in your best interest to go ahead and take a look at the graph and see if you can determine the range from the graph. And the range on this one, again, I would recommend that you, because we will go over this later in this class, is to just use a graphing calculator or a graphing utility for that. And what this would be is y such that y does not equal 1. And so that's the range. It would look like this, from negative infinity to 1, union between 1 to infinity. And again, this is the reason why I'm not a fan of interval notations once I start pulling out values that it can't be. So let's take a look at D here. For D, we have 2 things that are going on. So first of all, we talked about the denominator. We know that the denominator is going to have this restriction. I said x minus 6 greater than 0, and so x has to be strictly greater than 6. So the numerator, however, so this is coming from the denominator. The numerator, I said it greater than or equal to 0, and so x has to be greater than or equal to 4. Now, who's going to dominate? Well, obviously, that the denominator has to dominate because I can't have 5. If I put 5 in right here, I'm going to get a complex number. And so this will dominate the domain. So my domain then is the domain of h is going to be x such that x is greater than 6. Interval notation is from 6 to infinity. The range of f, and again, I would recommend you go out and take a look on Desmos. Or you can just reason under the fact, what is the smallest value that can go in there? Well, the smallest value that can go in there is something close to 6. So we're kind of getting close to, I'm kind of getting close to 1, sort of. And then if you were to put 6 in, you're going to have, well, close to 6. So like 6.001. So what I'm doing is I'm doing this. I'm doing h of, I'm getting close to 6. So 6.0001 into this function. I have the square root of 6.0001 minus 4 over the square root of 6.0001 minus 6. So this is the way of doing it without a graphing calculator, but you have a scientific calculator, so you can do it this way as well. And this gives you a really large number, so we know we're going to be going to infinity. So we know as we get closer and closer to 6 that this thing is going to go to infinity. So we know at most it's going to go to infinity. So then we want to think about what is the least amount that can go in there. Well, this involves a little bit of calculus, which we will go through in Calc 1. So if you want to think about what's going to happen when this x goes all the way out there, you're going to get about to 1, actually. So as x gets really, really large, so if you were to now try using your calculator and you say, let's put in 1,000 into this, and so we have the square root of 1,000 minus 4 over the square root of 1,000 minus 6, this is going to approximately equal 1. But it's never going to ever get to 1. But it's going to get close to 1. And so your range for this is going to be y such that y is greater than 1, or you can do interval of 1 to infinity. So you can totally do it by looking at the graph, or you can do it by choosing values. We want to choose, and this is going to be a good skill set. Choose values close to what my restriction are, and then choose values way out away from my restriction, and that will help me decide what the domain and range is. Okay, so now we're going to read it off the graph. So as we read it off the graph, we want to start on the left-hand side for the domain. Here's where we start for our domain, and here's where we end. These are inclusive, so the domain on this would be x such that x runs between -4 less than or equal to x. Let me just erase this. So -4 is less than or equal to x, which is less than or equal to 4. Or I can do it as -4 to 4. Now the range, I start here. This is the first time looking left or right where I see anything. And I'm going to go all the way up to 2. Right here at 2, it is a nice smooth closed curve, so I get to include it. So I have the range y such that y goes from 0 less than or equal to y, which is less than or equal to 2. So in other words, I have 0 to 2. Again, I'm going to look at my graph here. First time I see my graph is right here. So I start at -3 and I end at 2 for my domain. Now notice at 2, this is an open dot, so I don't get to it. It's non-inclusive. So my x such that x runs between -3, but not including 2. Interval notation is -3 to 2. My range, first time I see it is right here. I go all the way up to 4. And you're saying, wait a minute, you see it 2 has an open dot. Yeah, 2 right here has an open dot, but on this side, when y is 0, that's closed. So my range is going to go from 5 to 4 inclusive. So this is going to be y such that y goes from -5 less than or equal to y, which is less than or equal to 4, or in other words, from -5 to 4. Now, here's some questions to ponder, and we can discuss this in class. Can the domain and range of a function be the same? Think about that. Think about some of the ones we did. Can the domain and range of a function not intersect at all? I want you to think about that, and we'll discuss these in class. Now let's talk about what a piecewise function, and why would we want to ever learn this? What a piecewise function is, it's a function defined by its domain. So this part of the domain, this piece of the domain will use this function equation, and then this piece of the domain will have a different equation to be used when I go to graph it or do anything with it. So these are piecewise. This is what it means to be a piecewise. As an example, say you're in sales. Say your base pay in sales is $10 an hour. We'll go with $15 an hour. Your base pay in sales is $15 an hour. So if you work 8 hours and you sell nothing, your pay is 8 times that 15. Of course, that's your net pay or your gross pay. It's not your net pay. You have to pay taxes on it. Now, suppose that you sell 100 items. Between 0 to 99 items that you sell, you get no extra pay. You hit 100 items in sales, then you get a percent. You get your base pay of $15 an hour, and then you get a percent of what you sold. This is an ideal piecewise function. It says, hey, this is what you're going to get paid if you don't sell anything. This is what you're going to pay if you sell stuff. And so we have to use a different way of calculating your pay. That's a piecewise function in real life. So here's an example of a piecewise function. So we have x squared when my input values are 0 or less. 4 comes out if I'm between 0 and 2, and negative x minus 1 for x greater than 2. So I have to decide where negative 3, 4, and 5 land. Well, negative 3 lands in this first domain piece. It says, hey, if it's less than 0 or equal to 0, use x squared. So f of negative 3 is going to be negative 3 the quantity squared, which is 9. Now, when I have f of 1, that lands in this piece of the domain. So f of 1 is going to be just 4. And then my last piece, which is f of 5, lands in this piece. And so I'm going to use that equation, which is x minus 1, which should be 5 minus 1, 5 minus 1, which is 4. That's how we interpret the piecewise function, is we have to look at the domain. We say, okay, this is my input. Which part of does this input align to the domain of my piece? And something to note, by the way, check that out. An absolute value function, which we're going to discuss later in this class, is really a piecewise function. If x is less than or equal to 0, or x is less than 0, it is negative x, the line y equals negative x. And if x is greater than 0 or equal to 0, it is the line y equals x. So how do we graph these wonderful piecewise functions? Well, what I do is I look at the domain, and then on my graph, I actually will put a dashed line to remind myself something is changing at the breaks in my domain. So if I'm asked to look at negative 3 for x less than 0, so on my graph, here is my axes. And I'm going to put in at 0. So I know something's happening at 0. So here's when x is equal to 0. That aligns to this. And then something else happens at 2. So I'm going to go over here to 2. And this allows me to remind myself, hey, I know I'm going to have to change at that dashed line. Something's changing in terms of my outputs. Anything on the left side of 0 or equal to 0 is going to be negative 3 out. So anything less than, so right here is less than, so it's inclusive, because of this being inclusive, is going to be negative 3. This is the line y is equal to negative 3. If I'm running between 0 and 2 is inclusive, 0 is not, I'm going to use this. So if you're like, I don't know how to graph that, totally cool. Do a chart. Do an x, and then the output that I'm going to use is negative 3 plus x squared. So I'm going to put in 0, 1, and 2 because it tells me to break at 2. So I put in 0 and negative 3 comes out. I put in 1, I get negative 2. I put in 2, 1 comes out. Now, this piece is non-inclusive, but it's right on top of the other one, right? So it should have an open dot there, but because the outputs are the same at that place, then I get to have a closed dot there, only because the outputs are the same. Had the outputs been not the same, then this ordered pair 0, negative 3 would have had an open dot at that point. But because it is at the same place where I have an inclusive, which is the first piece of my piecewise function, it is going to dominate. So this is what that middle piece looks like. And it's going to be a closed dot right here, that ordered pair 2, 1. Now, anything larger than 2, I'm going to use that equation. And again, if I'm not really certain what that graph looks like, I can always do an ordered pair chart. I'm going to start out with 2 for my x, and I'm going to have x divided by 2 minus 1. So if I put in 2, I have 2 divided by 2, which is 1. 1 minus 1 is 0. So the ordered pair, at the ordered pair 2, 0, because it is non-inclusive, will be non-inclusive. So I'm going to go 2, 0, and I'm having an open dot right there. Because I'm doing x divided by 2, I'm going to choose even valued numbers. So I'm going to choose 4. I could choose 3, but I want to make my life easy. 4 divided by 2 is 2 minus 1 is 1. So I'm going to go to 4 and 1, and that's going to look like that. So that's that part of the graph. So there is a graph of my piecewise function. Once again, I want to look at which piece I want to use when I evaluate f of 1, f of -5, and f of 10. So if I am doing an evaluation of f of 1, it's going to land right here. So I'll use this piece. So f of 1 goes right here. In fact, let me use it in blue because I want to do that color association. So I'm going to use this one. So f of 1 is going to be -3 plus 1 squared, which is going to be -2. -5, well, where's -5? Well, -5 is going to land in this piece. So f of -5 is -3. And then my last one, well, 10 lands right here. So f of 10 is going to be 10 divided by 2 minus 1, which is going to give me 4. And I'm going to let you do this one on your own. You're like, wait a minute, why? Well, what's happening? Let's do a little bit of algebra. I'm just going to start the algebra. I'm actually going to start your graph here too, but I really want you to try this one on your own. So we know that something's happening at -2. So at -2, I'm just going to write a dashed line. So I know at -2, something's happening, something's changing. If I take this numerator, which is x squared minus 4, and I factor it into x minus 2, x plus 2, divided by x plus 2, look at my x plus 2s, and I end up with x minus 2. So I lied. I'm going to just do this. I was like, I'll let you guys do this. This is actually a really cool function. This x plus 2 is a removable discontinuity location. The removable discontinuity is we take this denominator. Remember, this is connecting up our domain. Our domain is x such that x cannot equal -2. The domain for this piece. That's why bringing this back in brings back in -2, but it says, hey, if you have it at -2, 3 is your output. So all of that. So how does this graph? How does this look? Well, let's go ahead and graph this. So I'm going to graph x minus 1, which is a linear equation, the slope of 1 standing at -2. And so my graph for this is here's -2. I have a 1, 1 slope, and so it's going to look like this. When I come down to this dashed line, I have a hole here, and then I keep moving. So that is the graph of the first piece. Now the second piece says if I have -2, my output is 3. So I'm going to go up here and I'm going to put +3, and that takes care of that piece. Now the evaluation is pretty straightforward. We either use the top equation. These two will use the top or the first piece of the piecewise, and this one will use the second piece of the piecewise or the bottom piece of the piecewise. So here's a question. Can more than one formula form a piecewise function be applied from a piecewise function be applied to a value in the domain? Something to ponder. We'll talk about this in class as well. And that's it for this video.